Chapter 8 is on logs and log functions. Welcome to the amazing world of logs. So section 8.1 is just giving you the basics of logs, because just like exponents, we have rules that we use for those, and properties. There's also rules and properties for log functions. If you think of a log as just being a switched around exponent, it'll be easier to know how to work with them. So it says the inverse of any exponential graph is the logarithm. Okay, so inverse of an exponent is a log. That's it. That's the basics of it. So it says if you have y is equal to ax, its inverse is x is equal to log ay. So basically what you're trying to do when you're working with a log is you're trying to find out what is the power. What would the power have been to get you that answer? So we've been doing trial and error in the last section with the ants and with the compound interest questions and the question about the chemical that's in smoke detectors. We were just doing trial and error and graphing them, but you can actually use logs to solve these. So if you take note here, your y, or your answer, is equal to the base and the power. Base to the power. The inverse then, when you write that, is you have the power is equal to log a, and this is important. It is not log a, it is log little a. Okay, so that's called a subscript a because it's lower than that, to the y. So your y, your x and y basically are switching sides, and your a is a little lowered a. So it says when we're dealing with logarithms, it means that we're looking for an exponent. Okay, we're looking for what is the exponent, or what is the power that gave us that answer. So for example, this log 981 equals 2 is read as log of base 9 of 81 is 2. So log base 9, and you don't really need to have that first of in there. You could just say log base 9 of 81 is 2, which means 81 is the second power of 9, or 9 squared is equal to 81. Okay? So log base 10 of x means that what we're looking at is 10 to the power of what will give you x. So this one, this log base 10 of x, is what we call our common log. And often it will be written just as log x. So if you ever come across an equation where there isn't a little subscript value there, then that means it is the common log, and that means that the base of it is 10. If you have questions that say ln of x, this is called a natural log, and you deal with it more in calculus. So what that is saying when you work with it, this is log base e of x. And we don't do anything with it in this part of it, but in calculus you will be dealing with natural logs. So, changing between logs and exponents. So if you're starting with an exponent and you want it to be in a log, remember this is like saying y is equal to a to the power of x. So using our form here, the y goes to the right of the log, Your a value is your base, and your x is what everything is equal to. So this one would be, because your x is a 2, so this would be 2 is equal to log. My a value is a 3, so that's base 3 of 9. So basically what you're saying is 3 squared is equal to 9. So the question is asking you, if the 2 wasn't there, it would be asking, what exponent of 3 will give you a value of 9? For the next one, we have 2 to the power of negative 2 is equal to 1/4. So we're taking a look at y is equal to ax, and we want to change this into x is equal to log a of y. So if I take a look at this one, my a value, or my base, is a 2. My y, what does this equation equal? Is equal to the 1/4. And my exponent is a negative 2. So that means that this would be written as negative 2 is equal to log base 2 of 1/4. And you could flip that around. You could say log base 2 of 1/4 is equal to negative 2. Either way is okay. So basically what it's saying is then 2 to the power of what will give you a 1/4? Well, that power has to be a negative 2. I just have to pause for a second. Sorry, I had a phone call. Okay, so the next one, 8 is equal to 2x. So if it helps you, do that. Label what are your a, x, and y values. So my y value for this one is an 8, my a value is a 2, and my x, or my power, is equal to x. So that means if I write this in, x is equal to log ay, x is equal to log 2, 8. Okay, to go in exponential form then, so we're going to go backwards. We're going to go from log ay equals x to y is equal to ax. So if I take a look at this one, my a is equal to 3, my y is equal to 9, and my x is equal to 2. So this is saying 9 is equal to 3 squared, or 3 squared is equal to 9. So in this question here, my a is a 3, my y is a 127, and my x is a negative 3. So we're saying 3 to the power of negative 3 is equal to 1 over 27. Next example, log of 4, so my a is a 4, my y is an x, so you have to be careful with this because sometimes they'll do that. They'll put the x and the y, but it's just a variable. You can write them any way, you can use any variables you want. It's just the placement of it. So this, as long as you always remember, no matter what variable they put there, that is always your answer to the exponent. So your x value is a 3. So this would be x is equal to 4 cubed, or 4 cubed is equal to x. So that's just switching them from exponential to log to exponential. So now if you want to actually evaluate them. So this question here is saying, okay, what is my x value? So my base is a 5, my exponent is an x, is equal to 125. So that's what you're thinking. What is my exponent that will get me 125? So in this case, x is equal to 3. 5 cubed is 125. And this again is where that little chart that you have with all of the up to the, I think it's the powers of 9 are on there. This will be helpful for this. So log base 3 of 729. So 3 to the power of what is equal to 729. This is my y, this is my a. I need to find my x. So your answer here is x is equal to 6. Log base 4 of 1 over 256. So they're saying 4x, 4 to the power of what is equal to 1 over 256. So that would be a negative 4. 4 to the power of 4 is 256. To do the flip, you need a negative exponent. Okay, so now this one is asking you to find what is your answer. It's giving you the base and the exponent. Now find the answer. So this is saying 10 squared is equal to what? And again, you have to watch here because sometimes in these questions, even though they put an x in there, in the general form, that spot there is saved for the answer. So 10 squared is equal to x, so your answer here would be 100. This one is asking you what is the base. It's given you your y value. You don't know your base, and it's given you your exponent. So it's saying a to the power of 8 is equal to 256. So basically, what you're going to do, I put an a, but you could have an x there. In order to get rid of this power of 8, you're going to have to do the 8th root. So on your calculators, you can do that. So that would be your, I'm just going to make that an x so it matches the equation. X is equal to 2. So then what that's saying is 2 to the power of 8 will equal 256. And you can check that and see that it does work. So this says log equations. We're still dealing with, it's in the log form, but we want to solve by writing it in exponential form. So again, always remember that we're looking at y is equal to a to the power of x. This is your a, so my a here is a 5. My y is x plus 3, and my power, or my x, whoops, shouldn't be a 3, that should be an x. So I have 5 to the power of x is equal to x plus 3. Not power of x. 5 to the power of 5. My x value is a 5. So in order to solve for x, I have to evaluate. 5 to the power of 5 is 3,125 is equal to x plus 3. If I subtract 3, 3,122 is equal to x. So log base 7 of 3x plus 1 is equal to 3. Here's my a, here's my y, here's my x. So 7 cubed is equal to 3x plus 1. 7 cubed is 343. Oh, I can't make 4s. 3x plus 1. Subtract 1, so 342 is equal to 3x. Divide by 3. 114 is equal to x. So this question, the next question says, what are the x and y intercepts of y is equal to 3 times log 2 of x plus 4 minus 21? So remember, for x-intercept, that means that your y is equal to 0, and your y-intercept means your x is equal to 0. So there's going to be 2 solving in here. So if we're going to find our x-intercept first, we're going to have y is equal to 0. So we have 0 is equal to 3 times log base 2 of x plus 4 minus 21. So the first thing I'll do is pull over my 24 is equal to 3 log base 2 of x plus 4. Divide by 3. 8 is equal to log base 2 of x plus 4. Okay, so then change this into exponential. I have a base 2, an exponent of 8 is equal to x plus 4. So then I just solved 2 to the power of 8, and I'll just continue it up here, is 256 is equal to x plus 4. Subtract 4, 252 is x. So that is your one solution. Your x-intercept then would be here at 252 and 0 if they need it as a coordinate. Your y then, you let your x equal to 0. So I have y is equal to 3 log 0 plus 4 minus 24. So same thing, I'm just going to solve. 24 is equal to 3 log 0, oh, that should be base 2, of 4, divide by 3, oops, divide by 3, so that gives you 8 is equal to log base 2 of 4. Oh, hang on, sorry, I'm going to pause. I went too far in my solving. I have to evaluate before I can solve that. Sorry. So my substitution part here is okay. What I have then is y is equal to 3 log base 2 of 4 minus 24. So what you want to do in that case, and I just jumped ahead too far, is I want to evaluate. So what is a log base 2 of 4? What would my x value be for that? So it's saying 2 to the power of what will give me 4. So I know in that case, my x is a 2. So that means that this, I can substitute, instead of saying log base 2 of 4, I can say y is equal to 3 times 2 minus 24. So 6 minus 24, y is equal to negative 18. So I have to do an actual evaluation of this one, because when I've got that log base 2 of 4, I don't have any variables left to solve for there, so I need to actually find out what is that answer. So it would be like in the last unit, if you had cos squared theta plus sine squared theta, you wouldn't leave it like that. You'd say, oh, cos squared theta plus sine squared theta, if you simplify it, equals 1. Okay, so just like our trig that we did last chapter had identities to work with, so does the logs. And if you want to think of these, the identities are they're also properties. So when we worked with exponents, we had properties. So when you had a power to a power, you multiplied them. When you had a powers being with the same bases being multiplied, you added the exponents. Same type of identities will apply to logs. So log base 10 of 10. So this is saying 10 to the power of what gives you an answer of 10. Well, that's just a 1. So log of 5, log base 5 of 5, 5 to the power of what gives you a 5? That's a 1. Log base 23,846 of 23,846 is a 1. So you can see there's a little bit of a pattern here. When the base and the y value are the same, so if the a and the y value are the same, then your answer is just going to be 1. If I have log base 10 of 1, so this is saying 10 to the power of what gives me a solution of 1. That's a 0. 5 to the power of what gives me an answer of 1? 0. 23,846 to the power of what will give you a 1? 0. So no matter what your base is, if your y value or the solution value is a 1, then that means that the whole log is equal to 0. So in this example here, if I had log base 2 of 2, then that would have equaled a 1. If I had log base 2 of 1, then my solution there would have been a 0. So I could substitute those in. So these are two basic identities. When the base and the y are the same, then your solution is 1. When your when your solution is a 1, then your exponent is equal to 0, or the whole log is equal to 0. So if you, identity number 2, if you're raising an exponent to a log and then logging and an exponent, then there's a rule that applies to that. So log base 10 of 100, if I look at this, this is saying just at the power here, log base 10 of 100. So 10 to the power of what equals 100? Well, that's a 2. So I can solve that to say that this is actually 10 squared. And 10 squared is just 100. So if I take a look at the next example, 5, if I look at just the exponent, 5 to the power of what is equal to 125? So that would be a 3. So this is the same as saying 5 cubed, which is 125. Log base 3 of 243, 3 to the power of what is equal to 243? That would be an 8. So this would be 3 to the power of 8, which is 243. So the pattern here, if you look, is 10, log 10 to the 100. Your answer is just 100. So your solution here is the same as the solution there. So when you're raising a power, and the base of the log and the base of the power you started with are the same, then your solution is just that y value in there. And it gets a little confusing here because I substitute the x and the y's, but it's just the solution to your exponent. So here I have an a, that's my base of the whole thing, and my base in the log are the same, then my answer is just my solution. So what happens there is the log and the exponent that's raised to it cancel each other out because they're just the inverse of each other. So an exponent raised to a log will cancel each other out. And that's because they are inverses. So if I look at the first example there, I would have 10 to the power of basically like that. So what's happening is this and this are canceling each other out and leaving me with that answer. So in this one, this would be 5 to the power of 5x is equal to 125. So my 5 and my 5 cancel each other, leaves me with 125. So whoops, I kind of went up there. So let's try it the other way. If I have log of 10, log base 10 of 10 squared, that's like saying log base 10 of 100. Well, so 10 to the power of what equals 100? 2. Log base 5 of 5 cubed, that's log base 5 of 125, which is just 3. So again, your base and your base are canceling each other. Your log base 5 and this 5 are canceling each other. So then your solution is just whatever the power was. So log base 3 of 3 to the power 5, my base and my base will cancel each other, so my answer would just be 5. So when you have log a of a to the x, so when your bases are the same, then your answer is just the exponent. Okay, so this says, determine the value of each without using a calculator. So this one, log base 3 of 27. So what you're looking at is, what is my exponent that's going to get me a base of 3, or what exponent when I have a base of 3 will get me to 27? Well, 27 is the same as saying log 3 of 3 cubed. So again, what happens here, according to this log identity here, is my base and my base cancel each other. So my answer is just 3. if I would have done it the other way, where I would have said 3 to the power of what equals 27, well then, that's 3 cubed. So log base 5 of square root of 5. So again, if I write this so that I don't have any, or I have the same bases here, this would be 5 to the power of 1/2. So my log 5 and my base of 5 cancel each other, so my answer is 1/2. Log base 2 of the cube root of 64. So if I rewrite this, cube root of 64 is the same as saying 64 to the power of 1/3. So 64, so that it has a base of 2, would be log base 2, 64. 2 to the power of what will get me that? Well, that's 6. So this is 2 to the power of 6 times 1/3. So my log base 2 and my 2 will cancel each other. What I'm left with is 6 times 1/3, which is just 2. Okay, next one. Actual problem solving with these. An earthquake with a magnitude of 7.5 is measured off the coast of Vancouver Island. In the town of Tofino, an aftershock is felt with a magnitude of 4. How much stronger was the earthquake off the coast than the one in Tofino? So something you need to remember is when they're dealing with Richter scales, they're actually talking about a log scale. So Richter scale is in log. And in this case, it's using the common log of base of 10. So if they're saying something has a magnitude of 7.5, they're saying a log with a base 10 of 7.5. Sorry, 7.5 is equal to log base 10 of your value. So if you remember from the first page there, the common log just is 10 to is just with a base of 10. So that would mean that this, they're saying 7.5 basically is equal to log of base 10. So if you did that as an exponent, this would be 10 to the power of 7.5. So that's what it was at the one place off the coast. And if we want to see how many times more stronger that was than the magnitude of 4, then you're just going to divide. How many times will a magnitude of how many times stronger is a 7.5 magnitude than a 4 magnitude? So when you're dividing with exponents, you need to remember that you subtract your denominators. So 7.5 minus 4, so this is equal to 10 to the power of 3.5. So it's 10 to the power of 3.5 times stronger, or if you actually evaluate this, this would be 3,162.3 times stronger. Lemon juice has a pH of 4.3, and soap has a pH of 8.4. How many times more acidic is lemon juice than soap? So with pH, the higher the pH, the less acidic it is, right? So lemon juice is 4.3, soap is 8.4. So lemon juice on the pH scale is very acidic. Soap, this particular soap, is less acidic. So how many times more is this acidic than that? Again, you're working with natural logs when you're dealing with the pH scale as well. So this would be 10 to the power of 8.4 over 10 to the power of 4.3. So this is 10 to the power of 8.4 minus 4.3, which is 10 to the power of 4.1, And when you multiply that out, it's 12,589.3 times more acidic. So that's how many more times lemon juice is more acidic than this particular soap. Okay. So there's a couple of examples of problem solving. This next stuff is just going to be doing inverse. And we've done inverse of exponents before, but we're going to have to do inverse of logs. So there's just basically 3 steps to remembering how to do both of them. So when we're looking at exponents, and we've done this before in, can't remember what chapter that was, chapter 3 maybe? And we were graphing y is equal to 2 to the power of x plus 1. So if you're finding the inverse, we switch the x and y value. So this would become x is equal to 2y plus 1. So what we want to do in this case is we want to, because we had a value for that y number, what we want to do then is we want to isolate the exponent. So we want to get that y value by itself, which is what we did before. We wanted to get y by itself. So this is going to be x minus 1 is equal to 2 to the power of y. So now we can't do anything further with it if we tried to use our calculators or whatever. But what we need to do then is we need to rewrite this as a log. So if we're thinking of it as a log, here's our base. This is our base. Here's our exponent. And here is our y value. So as a log, this would be y is equal to log base 2 of x minus 1. So y is equal to log base 2 of x minus 1 is the inverse of this. So if we're starting at a log then, and we want to change it then into exponential form, would be the inverse of that, we use the exact same steps. Actually, wait, before I do that, I'm going to do this example. So y is equal to 5x plus 1 minus 4. So if I rewrite this, this is going to be x is equal to 5, y plus 1 minus 4. So I need to have just my power and exponent by itself. So that means I have to move my 4 over. So I have x plus 4 is equal to 5 to the power of y plus 1. So if I write this as a log now, I would have y plus 1, that's my exponent, is equal to log base of 5 x plus 4. Now this isn't done because I need to have that y all by itself, so I would be subtracting 1. So I'd have y is equal to log base 5 of x plus 4, and you put that in brackets, minus 1. Because otherwise you'd have x plus 4 minus 1, which would just be x plus 3, which isn't the same thing. Okay, so let's do it for going from a log to an exponential. So we switch the x and y first. So we'll have x is equal to log base 3 of y plus 2 minus 1. So again, I need to get it so that I have my base and my y value all by itself and my exponent on the other side. So I need to move my 1 over. So this will be x plus 1 is equal to log base 3 of y plus 2. So to take this into exponential then, this would be 3 to the power of x plus 1 is equal to y plus 2. So I bring that over. 3 to the power of x plus 1 minus 2 is equal to y. Okay, so now let's try this for another example. Y is equal to log base 7 of x minus 1 plus 3. So switch. X is equal to log base 7, y minus 1 plus 3. I bring that 3 over. X minus 3 is equal to log base 7, y minus 1. Put it into exponential. 7 to the power of x minus 3 is equal to y minus 1. So 7 to the power of x minus 3 plus 1 is equal to y. Or y is equal to 7 to the power of x minus 1 plus 3. So there is a bit of a pattern, but you have to be careful because when you're working with some values, like if you have fractions or anything in there, it's going to mess you up a little bit. But if you take a look here, my base became the base here, my x, and then it was the opposite sign from here. So in this first one, it was a minus 1, and in my equation, that became the power with the plus 1. My plus 2 here became a minus 2. My plus 3 here became an x minus 3. My minus 1 became a plus 1. So it's just switching the signs and taking whatever is being added or subtracted on as part of the exponent, and then the part that was within the bracket is outside. So that's all for the first part of our introduction to log functions.